Good morning, everybody. Welcome to our machine learning seminar. We restarted the seminar after some a bit longer gap, and now we have some plans for recurrent meetings, at least several ahead. Today, we have a pleasure to have a presentation from Adil Kabylda, who is a PhD student in the group of Professor Alexander Tkachenko from the Department of Physics and Material Science, University of Luxembourg, who will present quite interesting topic to the engineers, but not only engineers, about machine learning force fields for large molecules. The application area is quite maybe distinct from what some of you may be doing, but I believe the techniques that are used there can be interesting and encouraging to follow. So Adil, the virtual floor is yours. Please go ahead.
Yeah, thank you very much, and thank you for the invitation to talk here. It's always nice to present our work. So yeah, I'll talk about machine learning force fields for large molecules, and everything starts, I mean, in physics and in chemistry, with the Schrödinger equation that essentially allows you to get an answer to model all molecules and materials and give you all information about molecules and materials. But of course, it's intractable to solve it in its exact form. So there's a hierarchy of approximations that gives you different accuracies and acceptable system sizes. So from Hartree-Fock to MP2 to CI, you get you can model smaller molecules, but at a higher accuracy. And what we want to do is push this diagonal line to the right side, and the new technologies do that. So here you have different approximations, such as density functional theory and the force fields. And the machine learning presents a new front line that allows it to push this diagonal even further. So in quantum chemistry, you can generate new ansatses for quantum Monte Carlo algorithms. You can develop new density functionals for DFT, and of course you can do machine learning force fields that allows you to breach force fields efficiency, so accessible system sizes of force fields and accuracy of the underlying reference method, whatever you choose on here. And so this was the state of the art of machine learning force fields at the time I started my PhD 2021. So people could already model simple molecules, periodic materials, reactions, nucleotides, and some small peptides. And the state of the art was kind of here. And now in 3 years, it moved quite a bit to the right. So now already people can model some proteins in water up to 20, 30,000 atoms. Yeah, but so yeah, so this is the state of the art more or less now. And let's discuss machine learning methodology for molecular modeling in general. So what we want to have is so the first step is, as usual, construction of a reference database of reference structures and associated quantum mechanical data. Then you want to have, so you have these dots, and then you want to represent your structures, your molecules or materials in a way that it's suitable for a machine learning model to learn. So the second step is the representation of atomic environments. And the third part is the learning of potential energy surface of the molecules. And let's start with the first point. So in view of this, in 2022, we developed a new MD22 dataset that was a continuation of MD17 dataset of smaller molecules that were used to benchmark all of these machine learning force field methods. So this is a benchmark, and this MD22 is the next version that extends extends the previous one in terms of the system size and the flexibility. And here we have units of all four major types of biomolecules and a few supramolecules. So the way we generate our data set is we perform molecular dynamics at some level of theory, at some good reference level of theory at higher temperatures. And we generate different conformations of these molecules. So we have, from the proteins, we have tetrapeptide. From the lipids, we have fatty acids. For carbohydrates, we have tetrasaccharide. We have a few DNA-based pairs and some interesting supramolecules here. And it's good to see that during the last 2 years, people really adopted this data set, and it really drove the advancement of machine learning force field a little bit forward. Okay, yeah, and the second step is the representation of atomic environments, and then here I guess physics and chemistry modeling is a little different, or maybe not so different. So we basically have so if we want to model molecules and if we want to represent from our Cartesian coordinates of just points in space to a way that is suitable for machine learning to model to learn, we need to respect some simple physical symmetries of the molecules. So this is so-called physics-inspired structural representations. So we want to go from the structure space to the feature space, but do it in a way that preserves the basic symmetries of molecules. For example, if you have a molecule and you translate it along if you translate it, basically nothing should change in the molecule. Yeah. So we want this system and the translated molecule. When we map from structure space to feature space, we want it to lead to one point in space. Yeah. The same thing happens if we permutate, if we perform some permutations. So essentially, these atoms are the same, and if we change the indices, also nothing should change. So this also should lead to one point in feature space. And the same applies to rotations. If you rotate the molecule, again, the same thing applies. But it should be, at the same time, it should be complete, meaning that if you have different molecule, different structure, these two molecules are different, and they should lead to two different points in feature space. And another thing that is important for machine learning is the smoothness. So when you have a smooth changes in your molecule, this should lead to a smooth change in the feature space, because only in this way we can learn. In this way, the machine learning model can really learn something. Because if you have some roughness, it's always hard. And depending on how exactly you impose those symmetries, there was a whole hierarchy, the whole tree of different representations. This graph is just to say that there are a lot of different ways to represent a molecule that preserves all these symmetries. And we will talk in the following work. We will use one of the simple descriptors, which is called inverse interatomic distance descriptor, which is basically all inverse interatomic distances in the molecule. For example, for this tetrapeptide here, the descriptor looks like this. So it's just a matrix with inverse pairwise distances on all everywhere here. Okay, and about the covariance, I'll talk about this later. Yeah, and yeah, so this is our descriptor that we will use. And the third point is the regression or learning task. And here we will use gradient domain machine learning. So the way how it works is rather simple. So you have given a set of conformations of geometries and associated forces on these atoms, and we want to learn those, right? So we represent. So we write a kernel in a gradient domain. So we have this kernel, and we take the Hessian of it, And this is our kernel, and then we use a kernel-rich regression to learn these weights, alphas. And in the end, we have a force predictor, which can give us forces for some new arbitrary structures. And then if we want to get energies, we also integrate this and then get the energies. Yeah, so we basically learn all possible geometries and forces in our training set, and we can predict for new query, we can predict new forces and new energies. And this is what drives our molecular dynamics and all of our predictions. And gives us the way how molecules and materials move in reality. Okay. And one thing to mention here is as well, so this original method was introduced to 2017. Then people understood that you need to preserve some of the symmetries, and then you have also some about some of the symmetries of the molecules that you have in addition to these two. Okay, so that's the method that we use. And yeah, originally when it was introduced, it was only applicable to system sizes of a few tens of atoms, and it was giving really accurate results of subchemical accuracy. But as you know, the number of pairwise, correlation, so this is a matrix, so that's why number of interactions scales quadratically. And these are some of the molecules from MD22 dataset, just to show that the number of atoms and the scaling law. And if you want to model it with the best gold standard level of theory from quantum chemistry, you can do this up to 20 atoms or so. Then if you have a density functional theory, you can go up to 400, 500, maybe 1,000 atoms. Classical force fields, of course, go in much, much further than that. But the problem at the time was that the global machine learning potentials, global in a sense that it correlates all interactions in the molecule. So it was only applicable up to 30, 40 atoms or so. So with in this work, we introduced a new iterative solver about which I will not talk today, but basically we extended the applicability to few hundreds of atoms. And we could model all of the molecules on the MD22 dataset without any potentially uncontrollable approximations, because what people usually do, because of this quadratic scaling, they just impose a cutoff radius and only model interactions within this cutoff. And here we could model everything at an arbitrary length for the whole molecule. But yeah, the problem of quadratic scaling still persists. And if you visualize your tetrapeptide molecule as a graph, so here you have as nodes an atoms, and edges are the interactions between them. And of course, this scales quadratically. And for the tetrapeptide, you have 861 edges or features or interactions in the global descriptor. If you look at the short-range interactions that are within the cutoff, they of course scale linearly, and that's what people usually do. So they only look at the short-range interactions and neglect everything that is beyond a certain cutoff. And this scales linearly. And the quadratic part lies in the long-range part. So this is a challenge. I have to describe it in a better way without going to quadratic scaling. So what we suggested in this work is the use of the reduced descriptor. So basically, we just say that the global descriptor for large molecule is overdefined. So you don't need to go to the quadratic scaling, because in principle, you only need 3n minus 6 degrees of freedom to uniquely define a molecule. So we developed a way to go from the global descriptor to reduced one. And here, the short-range part remains basically unaltered, and the long-range part gives a much sparser graph and still gives you good accuracy. And how we go from the global to reduced descriptor? So we train an original machine learning model so ML original, and then we perform sort of sensitivity analysis. So we mask all interactions, all features one by one, and see whether the performance of the model decreases or not. So, for example, if we remove this feature and we see that nothing really changes and the model is still accurate, it means this feature is relevant. We can remove it from the model. And if we remove one feature and the model suddenly performs much worse, it means this feature is important. So we rank the features according to the importance, and then remove every 10, 20%, 30%, and so on. And in this way, we arrive to the reduced descriptor. Okay. So before going to the big molecules from the MD22 dataset, we wanted to check on some of the earlier examples from MD17. And here we had an aspirin molecule, which is not so big, and we applied this methodology here. So here on the x-axis, you have a descriptor size, where 1 is the full global descriptor, 0.1 is a 10% removed, 20% removed, and so on. And on the y-axis, you have energy and force errors for the models with training size 500 and 1000. I only kept 2 for the simplicity, but it works for any training size. So what we observed is that actually when you apply this methodology to a small molecule, your performance is gradually decreasing. So your errors are increasing as you remove more and more features. And this makes sense because the molecule is small and all of the features are important, and it's not really applicable here. But surprisingly for us, what we observed for 42-atom tetrapeptide is that you can actually remove up to 60–70% of the initial global descriptor, and not only you gain some efficiency during molecular dynamics, gain speed, you also gain some accuracy, because the global descriptor is overdefined, there's a lot of noise, and now as you remove non-important features, more attention can be brought to the important features. So that's why the accuracy is increasing a little bit. And yeah, we can remove up to 60–70% for the tetrapeptide, which was a really cool thing. And then we apply it to some other molecules, and in all of them, you can see that even for buckyball catchers, one of the biggest examples with 148 atoms, we can remove up to 80% of the descriptor, of the original global descriptor. So we can say that these findings are general, and I will later show you some more justification of why and how exactly it works. Okay. So it's known in the community. I mean, it became more and more apparent that actually energy and force errors, if you look just only at them, they can mislead you, because the actual molecular dynamics of the system might be different. And that's why we did a different test here. So we actually performed steered dynamics between folded and extended state of the tetrapeptide. So tetrapeptide is a molecule that during molecular dynamics, it folds and unfolds. And just to speed it up, we also applied a force to the 2 terminal atoms in the opposite direction to make it unfold. And we have a few 2 references here. So in gray, we have a density functional theory, which is one reference. And in purple, we have a density functional theory with long-range corrections, with MBD correction, many body dispersion correction. So this is just 2 reference levels, but one with additional inclusion of long-range interactions. And we can see that during, so here on the axis, we have the time of the simulation, and then on the y-axis, we have a gyration radius of the molecule. Basically, this measures the compactness of the molecule. So we start with a compact structure, then we unfold it to higher gyration radius. And when you do it without long-range interactions in the reference level, the model unfolds, the molecule unfolds faster, because the long-range interactions are more often attractive. So they try to keep the molecule folded. So that's why it's easier to unfold. When you have EB plus MBD, meaning density functional theory plus this long-range correction, it takes a longer time to unfold. And here we compare the original global machine learning model SGDML in blue and the green one, which is a reduced one. And we see that both of them agree very well with the underlying reference. So both global induced models agreed well with the reference with the long range interactions, meaning that we do describe them pretty well. And another thing we did is performed a very long molecular dynamics of this tetrapeptide. So the potential on the surface or the conformation of the molecule can be basically described by 6 dihedral angles along the molecule, and they can be visualized in so-called Ramachandran plots, where you have one angle here, and there's 6 angles. You have 3 plots, and this is the way how molecule moves during molecular dynamics. And on top plot you have the reference that we have in the training set, which is 85 picoseconds. And you can see how it looks. And below that, in the bottom part, is our GDML with the reduced descriptor, and we run the dynamics for 50 nanoseconds. And these time scales are really they cannot be performed with the reference level theory because it's too expensive. And this we can do in days. So this talks about how we can really extend the time scales of our simulations with these methods. And the way how it actually, resembles the reference and describes the potential energy surface and all the minimas in the correct way. Okay, so yeah, we want to understand also why exactly this works, right? We see that the energies and the errors are smaller. We see that the dynamics is good. But why is it better? So in GDML, we can extract the so-called interaction heat maps, which are basically the contribution of atom I to the force prediction on atom J. So all of them is just basically interaction between 2 atoms, and they're averaged over 1,000 configurations from the training set. And on the diagonal, where we have indices that are close to each other, you see that contributions are higher, and on non-diagonal elements, especially in the corners, everything is kind of dark, meaning that the interactions are very small. And if you compare this global model to the local model with the imposed cutoff of 5 angstrom, you can see that almost everything beyond the diagonal elements are excluded completely. So the contributions are 0. And the reduced model that we developed offers an improvement over both global and local descriptors. So we have at the same time a very good description of the local interactions, but we also keep some of these non-diagonal elements in the corners that the model thinks are important. And if you compare this to the tetrapeptide molecule and these atomic indices, as I said, during molecular dynamics, the molecule folds and unfolds, and indices of these two ends actually correspond to the diagonal elements here. So even though the interactions are very small and rare and rarely happen, the model needs to keep the information about the distances of these 2 ends in order to generate a reasonable molecular dynamics. And that's what our model spots and spots here, yeah, and preserves this weak, long-range, rare interactions. Okay, and the same applies to all of the molecules, and this is just to show that the descriptor is non-trivial, and it's hard. You cannot do this in any. With any chemical intuition, it's very hard to do it. So the descriptor is always non-trivial. Yeah, and from the machine learning point of view, we can also look at. So as I said, each entry in this matrix is actually an average of 1000 configurations. And if we take one entry here and expand it, so here we have a contribution to the force prediction and the distance. So we have this 1000 interactions of two atoms, which in this plot are averaged into one entry. Here we expand it, and we look how this contribution decays with distance. And we see that some of the features in this interaction, some of the features are actually linear. So we have R squared of close to 1, and the slope of -2, which suggests that it's a Coulombic interaction of two charges. And it's pretty linear. But some of the interactions are actually just a blob. So they have zero correlation with the distance, and it's just basically a noise to the model. And so the features in the global model can range from linear to stochastic with respect to the interatomic distance. And what we saw that in the global model of the small molecules, such as tetrapeptide, here we have this coefficient of determination for each feature, and here we have number of features, so just a histogram. So in the tetrapeptide, almost all of the features are linear, and you see it's a big last bar here and a long tail. But when you look at larger and larger molecules, you can see that there's more and more stochasticity in the regional global descriptor. And if we do the same for our reduced model, we can see that we basically remove this noise, and our model features in the reduced model are almost exclusively linear. And of course, it still has a tail because it's not a linear model. I mean, the dynamics of the molecule cannot be described as a sum of linear terms, and you cannot get rid of these stochastic features. But in any case, we remove most of them, and that was what also justifies why this works. And last but not least, for me as a chemist, as a trained chemist, it was important to look at the actual molecules, yeah, and what interactions are kept from the chemical point of view. And here I visualized this in the following way. So in the global model, if you select this yellow atom, this hydrogen, in the global model, all interactions are kept. So the interactions that are kept are in purple. So in the global model, yellow interacts with everything, and everything is purple. Now, as you go to smaller and smaller descriptor, you can see that some of these things are disappearing. And in the most reduced model, surprisingly for me, for example, because I expected that if you select this atom and you just select the most important features to the model, this would be just within the cutoff radius here. So with this atom and maybe this, and that's all. But in reality, what matters to the machine learning model is actually features along the chain of the tetrapeptide. So the conformation of the whole molecule is more important than this second neighbor. So of course, it keeps the first neighbor, but these are more important than these short range features, which was cool to see. And of course, it depends on the molecule. So if we have a molecule here, we have a disaccharide. So during the molecular dynamics, the molecule it's not really flexible. So it just vibrates around the global minima. Nothing really happens. And in this case, you can really describe your system with some kind of cutoff radius here, and neglect all interactions beyond that. And this what also justifies the success at the time of machine learning models when applied to materials, because in materials it's not really flexible, it just vibrates. And in this case, the locality assumption is really justified and really comes into play and to the benefit of the model. But when you have something more flexible, it looks quite different. So, for example, here, if I select a carbon atom in the main chain, it can be described with some kind of cutoff. But for the hydrogen, since it interacts with some atoms farther away, it's really non-trivial. And my favorite example here is this buckyball catcher. So it's called buckyball catcher because I have like a ball, and the catcher, like the catchers from the baseball, right? And the long-range interactions are actually keeping the ball inside of the catcher, so we cannot fly away. So it just rotates around this catcher. The ball just rotates. And when you look at the, if you select any of the atom on the ball and see what's important for it, you of course see that some of the covalent bonds and bridgings in the ball is important, but only a few of the features from the catchers are kept because you don't need to know about all of them to understand the distances and yeah, to understand how far away the ball is from the catcher. So you just only need to keep a few of them, and vice versa. So if you select any of the atoms in the catcher, you keep some of the local environment, some of the features from the other hand, and only a few features from the ball which are around the ball, which gives you information about how it is rotated and where it is. So these patterns overall are explained by combination of the strength of the interactions from physical point of view, but also about the statistical information these features provide about the atomic fluctuations. Okay, and we came to our conclusions. So basically what we did here is we escaped this quadratic scaling for global model and drop down this nice green line here to the linear scaling. We just demonstrated potential for linear scaling in global models. We analyzed the non-local interatomic features that contributed to accurate predictions, and we see that these are even beyond 15 angstrom, and 50 angstrom is basically a diameter of our molecule. So we have bigger molecules. I think we would have even, features that are kept would be even further away. So, and for some cases, this locality assumption is justified, but here we show that for other cases, it's not. And yeah, we try to understand interatomic interactions from machine learning point of view. And yeah, I have to thank, I actually want to thank the Luxembourg National Research Fund that funded my PhD, and the HPC that helped calculate all those things. And the results that I presented here, they are in these two papers that you can check it out. And yeah, thank you for your attention. I would be happy to answer your questions. Thank you very much.
Thank you very much, Adil. This was a very nice and insightful presentation. Before the question and answer round, let me do what I forgot to do in the beginning, to introduce Elisa GÓMEZ DE LOPE, who is now collaborating with me to support the running of the seminar series. She's a postdoctoral researcher with the computational engineering group at the University of Luxembourg, and she can be contacted on any topic related to the seminars, the same as I could. So thanks, Elisa, for agreeing to join the organization team. And yes, and let's now go to the questions round. I have several, but as usually, I will leave the floor to others to ask questions. Please go ahead to switch on your mic or raise hand, whatever you wished.
Yeah, please don't hesitate. I really like questions.
Okay, so let me ask a warm-up question first. So this will be a bit technical, but this was something that always was coming to my mind when I was looking at those approaches that you presented, especially related to the selection of the feature space. So you have all pairs of degrees of freedom are described there in this feature space, right? The input to make it frame indifferent, right? In the most basic approach. So you computed the inverse of the square of the distance, right? And this was somehow your input to your neural network or machine learning model. And my question is, how do you usually deal with the fact that the order of the degrees of freedom is quite arbitrary. And normally you can have the factorial of n permutations of the degrees of freedom, which creates your input quite difficult to manage if you think about a particle, a new particle that you want to consider. How do you decide what is the order of atoms in order to make it manageable by the neural network model?
Yeah, so thank you for the question. So the order of the atoms are of course important, along with all those symmetries that I mentioned. And in this kernel-based approach here, in the gradient domain machine learning, in the original approach there was no order. So basically, if you have, for example, like three atom, for example, in this CH3 molecule, you have 3 hydrogen atoms that are basically equivalent, and if you change the indices, nothing really happens. So in the original approach, this was missed, but later, as people understood that you need to include more and more physics, this was of course remedied. And in case of the GDML approach, this resulted in a different algorithm that detects the symmetries and adds a new sum along those symmetries here. So in addition to this, you have a new sum. So in this way, this was taken care of. But of course, in the next approaches, in the following approaches, in the graph-based message passing neural networks, this is handled automatically because you have all these equivariances and even higher order symmetries. Yeah, so the kernel-based approach, where we have a matrix, we just have an additional sum of symmetries here.
But let's say that somebody would just switch the indices of those atoms. So I don't mean the symmetries, just one atom and the other atom, and that the representation of the particle would change by switching the indices. So the whole matrix will be shuffled.
Yeah. But here in this sum, I have all terms, so with all switchings, right? So I sum over all of them.
I see.
Yeah, and it's okay for the matrix because from the interaction point of view, these are the same things. So when you learn it, it gives you a really good advantage. So essentially, these rows in the matrix of interaction, for all these 3 systems, it should be equivalent.
I see. So the output of the neural network model is the energy, in fact, the scalar.
No, it's forces. It's forces.
Okay.
The output of the model is forces.
I can
3
okay.
and forces.
Okay. Thanks. I saw some people were switching on their mics. So is there any question?
I have a question.
Yes.
I can ask it. So you mentioned that one of the models or the type of models that you're using are message passing neural networks. I'm guessing it's graph neural networks.
Yes.
So did you try different architectures or different types of message passing neural networks? And how do you account for this symmetry, for the spatial properties or symmetries in these models?
Yeah, so our approach is applicable to global. So we want to study the global machine learning first, which do not have any cutoff radius. So what people do in graph neural networks, message passing neural networks, they say that if I choose this atom, all the interactions within, I don't know, 5 angstrom of cutoff radius are important. So the messages are passed only between atoms within this cutoff. So I don't have, so the quadratic scaling problem is naturally avoided by just imposing a cutoff radius. And I mean, it's justified in some cases, but we wanted to check from the global model, which keeps all of these interactions and does not have this potentially uncontrollable approximations. So we applied it to a global model, and there's only a few of them, right? And if one talks about message passing neural networks, graph neural networks, they are kind of the next step in a sense. So if you, I mean, So yeah, just prepare this partial overview of machine learning force fields. And initially it was GDML and SNET, which is kernel-based and neural network-based approaches, which could model tens of atoms. Then in between here, people started to notice that the graph neural networks approaches are really good and natural for molecules. If you do not look beyond some, if you do not care about long-range interactions, and introduce so the spooky net, the GEMS approach, and now we're working on this Socrates model, which is even better than all of the things before. Yeah, and the question was how people account for these symmetries. So in yeah, so in this message passing neural networks, the symmetries are taken care of by the means of equivariance. So you just you just model some more spherical harmonics and stuff like this, and yeah, so just introduce a little bit more physics, and yeah, and that's basically.
So so if I understand well, then the message passing neural networks that you used in the approach that you presented are not using the graph structure.
In my approach, in the things that I presented, I use GDML, which is kernel-based model. It's not a graph neural network-based model. Yeah, so it's a kernel-based model.
Okay, thank you.
Yeah. But as I said, yeah, we're working on a new thing now, and we can talk about it maybe after summer when it's going to be published.
Sure.
Yeah, and yeah, and the permutations and graph neural networks, they're handled naturally because you have one atom and you describe each atom separately. So whatever you do with the, however you do the permutation doesn't matter.
Yeah. This is why I was asking, because
Yeah.
I'm not in this force field, but I've read some papers that those similar.
Yeah. These are really cool approaches, but the problem is this cutoff radius, right? Even when you have 2 or 3 message passings, you increase your, for example, you have a first message pass within 5 angstrom, then second within 10, and you have a perceptive field of, let's say, 15 with 3 layers, right? But the way how the information propagates, it's not ideal, so it's not actually 15. So you just have some vanishing information that does not really get to the final atom. And the second thing is that when you, we of course want to go to bigger molecules, to proteins, to I don't know, 100,000 atom systems. And there, this locality assumption is really not ideal, even when you increase the perceptive field with message passings. So it's still an open problem how to describe these long-range interactions here. Yeah, and GDML approach, in a sense, gives you some information of how machine learning models look at those interactions, right? They give you some some idea of how to do it in general, because they're global, from the start.
I see. Thank you very much. Interesting.
Have you been considering the different architectures from the graph, like those attention-based architectures that are very popular nowadays?
Yeah. So actually, Socrates uses some of the things from the attention and from message passing neural networks. We are collaborating with machine learning group from TU Berlin, and it's always a nice thing when they help from the machine learning point and we help from the physics chemistry point, and we want to tackle some big challenges in the field with expertise from both sides.
Very nice. Stefan, I can see that you have some question in your head. No?
Yes, I think there was a disconnection. I don't know if it's on my side or where it was, but I I could more or less hear
You appeared
what you
somehow.
just said, and I thought this is
Visual.
directed at me. Thanks. Yes. So thanks a lot for the presentation. I have no specific questions on the actual application itself because I don't understand it well enough.
Yeah.
But I would have questions on a more general problem. So if I understand correctly, you're trying to fit, I mean, a highly nonlinear functional that has a bunch of inputs and is going to spit out some sort of output, and the dependence on between the input and the output is highly nonlinear. Is that a good summary of what you're doing from a more abstract point of view?
Yeah, we want to input the geometry of the molecule or material. We want to output some properties. Yeah, and the mapping is highly nonlinear, and the machine learning models, all different kinds of architectures are really good at learning those things. Yeah.
And what did people do before the whole excitement about machine learning? You know, so before, I mean, I'm not saying that there was no machine learning before, but I mean, you will probably agree that recently there was some sort of hype. So before that hype, what were people doing in that field?
So before that, one could say that. So it's a whole field of quantum chemistry, right? So we have the Schrödinger equation, which is too difficult to solve, and we have a bunch of approximations that gives you, that gives you the same thing, but at a very high cost, right? So we solve it with very expensive methods, and we get some high accuracy solution. And actually, the ML front, it is there, but it still needs this reference data from those underlying ab initio methods. So we still need to get a few of these calculations first, then we learn the mapping, and then we can apply to a system that, in a sense, close or maybe a little bit out of the range, right?
Yes.
So
Yeah. Sorry. Go.
Yeah, before machine learning, people just did quantum chemistry, and people still do and will do quantum chemistry because we need those methods anyway.
But sorry, in that direction. So did people not try things that are more standard, like model order reduction things with projections on linear spaces and stuff like that?
This was
I'm sure they probably did this, right?
You mean like coarse graining and stuff?
Yeah, I mean things like, you know, you have this nonlinear thing and you try to project it locally on some tangent plane to this nonlinear thing. Dependency, and then locally it's okay, but as soon as you drift away from this, and it becomes wrong, and then you need to adjust by doing more calculations depending on the conformation, I guess, of the molecule and the parameters that you do have. You know what I mean? So you would like have a tangent plane, and you would say the thing behaves like the tangent plane in the vicinity of that set of parameters, and then if you start getting too far from that, you need to correct it. So do you know if people did that before? And then
I would say that maybe people did that before, but probably unsuccessfully, because this whole field started more or less in 2007, 2010. And before that, either machine learning force fields, machine learning methods were not good enough. Maybe there was not so many computational power, and the potential on the surface of the molecules is really hard to learn, actually. And only recently this exploded, and it exploded at a very high pace. So the first, as I said, the first model 2010, 2007, and then we could get chemical accuracy for like drug-like molecules like in 2017. And then now we can model proteins in water and some really big materials like nanometer scale materials. And this is also, partly happened because of the fast advancement of the machine learning community, but at the same time, in our sub community, like machine learning forces and so on, people post everything online, so everything is open source. So by the time, for example, you submit, so we submitted this work 2022. It was published mid 2023. By that time, already one generation has passed, and every 2 years we have a really cool advancements. And this is partly happens because everything is open source, almost everything.
That's super nice. And then if you make, thanks a lot. I had no clue about this. So it's didn't know it was so recent. because in other fields where you have also highly nonlinear systems, people, I mean, have been doing all sorts of reduction for ages, and you know, and there is a whole field that came about, you know, to try to generalize the linear projections into some sort of nonlinear projection on some sort of curved
I guess for molecules it was too difficult, but I mean, I think the seminal paper was published in 2007, more or less. Yeah, but maybe I'm just not aware of anything before that. Maybe I'm just not aware of that. But
no, but it's good to know, because it's an interest. So it must be really a super hard reduction problem that has nothing to do with the others, I guess.
I mean, Schrödinger equation is is a mystery, and not a mystery, but yeah.
And then, sorry, a small question. Let's say that you have trained a network. I'm sorry if you already answered the question and I missed it, but probably I did. But if you already trained a network for, let's say, a certain case, let's put it vaguely like this, and then you see another case which is not too far from the ones that you have trained, and you try to predict it for a slight disturbance. How effective is this? And I'm sure you talked about it, but I just missed it.
No, I didn't talk about this, but the most recent methods are actually, very generalizable in a sense. So, for example, if you want to model all the proteins, you can cut this protein into small pieces, generate reference data for the small pieces and a little bit of the large pieces, and you make and you put everything in the machine learning model, and it makes a very good Frankenstein, and actually, I mean, really good approximations to everything that can happen with within this subspace of things, right? But I think now even people are even doing even more general stuff. So they train on all kinds of things and expect machine learning model to be applicable to everything. Of course, it doesn't work as well yet, but in principle, maybe, I don't know, some years from now, you would just have an oracle in which you could input any structure and it would give you very good, reasonable results.
Okay, so the idea is to do a bit of Lego block approach, right? Where you have
divide and conquer in a sense. And since we know most of the physics, we want to input all of this physics in the models as well. And yeah.
But then when you do this Lego block approach, let's say I take two. Of course, you have a cutoff radius, right? But if you take two molecules and you link them together, the interaction is also itself nonlinear. It's not just sticking things together linearly, right? Because they all talk to each other, right?
Yeah. So we want to, I mean, what we're doing kind of now is that we let the machine learning model take care of the local things, and we implement some of the methods that we develop in the group for the long range stuff. And this should be nonlinear and many body and stuff like this. Yeah, and of course, when you encounter some new configuration which is completely absent, as completely new, the machine learning model will fail because it only is good within and maybe a little bit beyond the training set. But in cases like this, you can just augment your training set with a few of the new structures and then retrain, and it should be just so. This is called active learning, yeah, and this is what also people do.
It's called active learning, okay, because that's exactly what I was referring to without knowing what it's called. Okay, thanks a lot. Thank you so much for being so engaging.
Yes.
Thank you.
Yes.
There is a question in the chat about
Exactly.
about
Yeah, can you yeah, I don't have the chat. Can you please?
Elisa, can you read this, because the speaker cannot see it when presenting?
So Qasim Ali asks basically about how you prepare the data set and if there is related data available, or in such case, if you think we can make something to simulate the results, something along these lines.
Yeah. So the data is generated by performing these ab initio calculations at the ab initio level with quantum chemistry methods, which are expensive, but you do those for some structures, right? And so what people do is actually they generate some structures with very inexpensive semi-empirical method, so that you sample all different conformations, then you select some of the most important conformations and do a really high accuracy quantum chemistry calculations for that, and then you learn on top of this. And you can generate for any system of interest. Yeah, if you want to model materials, you generate some of these materials data sets for nucleotides or whatever thing you can generate it. But at the same time, there's also a lot of already generated stuff out there. So a lot of data sets are published online, and depending on application, you can use those as well.
And now a question from myself, like so the data set you use is basically different conformations of the same molecule all the time, or different molecules?
So in this benchmark data sets that we have here, MD22, we have for each, so we have 8 systems here, 8 different molecules. For each of these molecules, we have several tens of thousands of structures. Okay, so we have different molecules and also many structures for each one of them.
Okay, I see.
And these are mostly self-interactions that you are looking at, right? Or you can combine 2 molecules together to. It is too far from the training data, right? If you combine 2. Lipids, for instance, interacting with one another.
With one another, yeah, I see what you mean. So if you learn only on one lipid, of course, it will not know anything about the other thing. But as I said, the field is advancing really fast. At this time, this was really state of the art. People could only model molecules, but even here, for example, you have 2 molecules. This ATAT is also two sets of pairs of DNA-based pairs. But in general, if you want to make it really general, you need a very big data set, and that's what people are doing now. So they generate data set with millions of molecules, all kinds of interactions, dimers, trimers, all kinds of things, and then just fit everything in the mold. And provided that it's big enough, it can run these things.
So it's the same model for all kinds of molecules.
So here, the things that I presented, this is system specific, but now people are developing more general things. Yeah, with yeah.
I see. Thank you.
I have a quick question.
Yes.
Yeah, please go ahead.
Yeah, I mean, because you were saying, let's say when you use, let's say the model you're training for molecules based, and you want to do simulations, you put on some external, let's say, van der Waals force between molecules, right? And you just use this force field for short range. How would you handle the short range repulsive force between molecules?
So there's the 2 ways to do that. You can just hope that the model learns. So if you have enough examples where molecules are close to each other, the energies are high. So you expect the model to learn that you have a repulsive force. And the other thing that people also do is that just implement one of the repulsive potentials from physics.
Okay.
Yeah, like ZBL can just impose those constraints at the very short range. Yeah, below like 1.5 angstrom.
Yeah, I see. Yeah, thanks. It's a very quick one. Thank you.
Thank you.
I have one question. Sorry, I jumped into the presentation a bit late, but could you please talk more about the kernels that you use, this Gaussian approximation potentials? Yeah, similar kernel-based methods and also model order reductions, and I was curious that you use any physics-informed information in your kernel.
So the physics information that we use in our kernel is, so we have these interatomic descriptors, right?
Yeah.
Which is this thing, and then our kernel looks like this. So we have the distance between 2 descriptors and some function that ensures that we can twice differentiate it. And what we do here is we take Hessian of this kernel. This gives us also directional information, and also, I mean, allows us to preserve some of the physics. Yeah, So we take Hessian of this kernel and learn on it.
a Gaussian kernel, you're multiplying with something and you're taking Hessian of that. Okay.
Yeah.
Okay, thanks.
All right, I think we should be slowly ending the meeting. Thank you very much for the presentation, Adil, and for answering our questions. And thanks to everybody for your attendance today and for asking questions and for a nice discussions that we had. Elisa and I will keep you informed about the future seminars that will come in this series. And for today, I wish you all the best for the day. And
thank you very much as well.
See you soon. Bye-bye.
Thank you very much. Yeah. Bye.